So I'd like to introduce our speakers, Aaron Grosser for Barr Engineering and Colter Schwagler from the DOT.
Hi, everybody. How many people in this room have had construction-related issues with adjacent landowners or homeowners on projects recently? Okay, just about everybody. One of the purposes of this presentation is to kind of go through, and while Colter and I are both geotechs, this is not going to be a geotech-heavy presentation. As much as I want to talk about how we stabilize the landslide, this is more about how we worked with the community and the community engagement to get through the construction phase of this project. I'm going to go through a little bit of the site history. We'll talk about the purpose of the project, how we characterize the site, and the stabilization design, and I can assure you there's only 3 geotechnical slides in here. But what's most important is the public involvement and some of the work that we did ahead of the construction project on vibration evaluations. And then a really important piece was how we brought in the community engagement and the public engagement as we walked through the project to make sure that we heard the concerns of the homeowners, the property owners near the site, and then we'll get into the construction and have a few conclusions on the project.
So just a little bit about the project location here. So the project occurred in West Fargo, North Dakota. You can see the specific project location on Main Street in West Fargo. The slide that we're mitigating is on the north side of Main Street on the south bank of the Cheyenne River. So a little bit about the geology of the area. This is occurring in the Red River Valley. The Red River Valley soils were deposited by glacial lake agassiz. So in this area, there's a large glacial lake at the end of the ice age. As the glaciers were receding to the north, the Red River, trying to flow north, was dammed, created a large glacial lake, which allowed clay particles to deposit, creating the flat plain that we see in the Red River Valley now. Then those clay particles are very soft, glacial lacustrine clays. That means they're very soft, they're very compressible, they're highly plastic, they have low shear strengths, which creates a lot of landsliding issues. So we actually have a lot of landsliding problems in the eastern part of the state, in the Red River Valley, and most of those are at river locations. So specifically the outside bends of the rivers. So you can see the Cheyenne River snaking through the picture on the left here. As the river goes from east to north on the kind of right edge of the yellow box, that's kind of the outside bend, creating some erosion issues and causing some instability in our embankment and the riverbank. So a little bit about the site history. So we've known about this slide for quite a while. The geotech section has had some level of monitoring for probably 20 plus years at this site. You can kind of see the scarp called out by some of those orange arrows on the project. The top right picture is kind of the scarp on the eastern edge of the project. So you can see several feet of set down in that area. In that area, there used to be some storage buildings. There's some storage buildings currently on site. There used to be more. They ended up having to be removed due to the significant landslide movement there. And one thing of note at this area is that we've done some recent construction in this area. In 2016, Main Street was reconstructed here, and then in 2009, we attempted to replace the Cheyenne River Bridge with a cast-in-place box culvert. We ended up abandoning that project. We ended up coming back with that 2016 project and replacing the bridge with a precast box culvert. So we've done some construction in some areas, some relatively significant construction relatively recently. Here's kind of a picture of the west scarp, and then the hatched area in pink there is kind of the demarcated slide that we're talking about. So as the slide kind of moves to the west, it gets closer to the roadway and then eventually into the roadway and the edge of the driving lane there. So like I said, we've kind of been monitoring this site for quite a while, kind of several series of instrumentation. One thing that we like to do when we're monitoring these slides that we maybe don't have immediate plans to fix is we like to drill some holes, get some soil characteristics, install some instrumentation, get an idea what the geometry of the slide is. Some of these we don't have plans to fix immediately or in the near future, but we like to have that information on hand in case something changes with the slide. It starts moving much more rapidly, it gets bigger, starts impacting more infrastructure, and it kind of turns into an emergency repair situation. It's nice to have that stuff ahead of time instead of scrambling to get some field investigation going. So with that, we had instrumentation installed on site for several years. On the left, you can see an inclinometer plot. So an inclinometer is a PVC tube that we put in a borehole, and we can use that to monitor the slide movement. So the idea is that the borehole is installed perfectly vertical initially, and then as the slide moves, it offsets different parts of that PVC pipe. So where it kinks out to the right, that's the slip plane. Everything above there is moving with the slide. So you can see how much it's moving, and then each individual line is a different reading of that associated with a specific date and time. So you can kind of judge how fast it's moving based on the amount it moves over time. Then on the right, we have a piezometer plot. So piezometer is another instrument that we install in a borehole. We install these at just one specific depth. They read the pressure of the water sitting on top of it. So then you can do a little calculation, determine the feet of water sitting over the top of it, and you can get your groundwater table through that. So this looks like it's varying a lot. This is actually only a couple feet. So at this site, it ended up turning out that the slide wasn't particularly sensitive to the groundwater in the area. So the groundwater in the Fargo area is really consistent. It's pretty much always 5 to 10 feet below ground. You can see here it's bouncing a couple feet seasonally, but that didn't really line up with changes in the slide movement. The slides in the eastern part of the state typically move when the rivers are kind of empty. So that river acts as kind of a buttressing force and kind of holds the slide in place during like flood events or when the river's running high. In the late summer, fall, winter, when the river's sitting low, that's when we see these slides move the most. So kind of as we're monitoring the slide over time, we're starting to notice some impacts to our infrastructure. Initially when we're starting to look at this, everything seems like it's kind of north of the road, not having a ton of impacts on us. We're just kind of keeping an eye on it, but some things start to show up. There's a storm sewer pipe that's outletting into the river there. That starts separating significantly, and then it's causing a sinkhole. So the slide has pulled that pipe apart, and then material is getting into there and washing out. And then additionally, on the right, you can see, or it's maybe a little hard to see, but our curb and gutter has started to drop significantly. We've kind of lost drainage in that area. It's starting to pull apart from the driving lane pretty significantly. The sidewalks dropped. We have some street lights starting to tip. And we know that scarp kind of goes into that driving lane a decent amount. So that driving lane is a little more significant concrete that's withstanding some of that slide movement at the time. But we kind of want to start looking at mitigating this before we see something move into the driving lane that is going to cause a little bit more concern. So with that, the department initiates a project. The concept of the project is we're going to mitigate the landslide. We're going to repair the damage the landslide has caused, and then that landslide mitigation is going to protect our assets into the future, both the North Dakota Department of Transportation's and the City of West Fargo's assets.
So the project was awarded to Barr Engineering Company and our partner SRF Consulting Group. And we've teamed on a number of these landslide stabilization projects. And for the design phase, Barr took the lead on the project, and we started with an evaluation of the existing conditions out on the site, where we developed 3 cross-sections through the site to look at what the extents of that landslide were and install some additional geotechnical instrumentation and grab some samples for laboratory testing. And you can see we picked something through probably the largest or the furthest extents of the landslide, and then another 2 cross sections heading more to the east. One of the things that is kind of critical is we've got to stabilize this landslide such that it doesn't slide and block the Cheyenne River, which would probably cause some flooding in the area. Excuse me, I've been losing my voice for 2 or 3 days here. So as part of our geotechnical evaluation, we did a seepage calibration and a stability back analysis, which is really important with these types of clays in the area. The site is generally overlain by the Chirac Formation, and then a softer, which is actually not that weak, Brenna Formation, and then the Argosville Formation, all over a glacial till at the site. So there's about 90 feet of material here, and what we typically see is a slides form within the Brenna Formation because it's much weaker. So we installed some piezometers in the cross-section so we could get a little bit better understanding of what the pore pressures were within the landslide, and 2 inclinometers here so that we can understand about where the base of the landslide was shearing. We did a seepage calibration to the average Cheyenne River elevation, and then we changed the permeability of the soil and the boundary conditions to match that piezometer readings on the site. And what's really important here is, as Colter said, is when the river level's low, that's when a lot of these slides occur. So we did a stability analysis, back analysis, where we took a look at the slide and used the instrumentation to do an analysis where the factor of safety of that slope was 1.0, which is basically incipient failure. So we know that the slide had moved. We can map out where we think that failure surface is from our instruments. And then once we get to a factor of safety of 1.0, we've got calibrated groundwater conditions and we've got calibrated soil strengths. And we can use that within a more sophisticated model where we developed a finite difference analysis. And we looked at a couple different ways to stabilize this landslide. One of them was to do a simple regrading program, and there really isn't enough room on this site to regrade the slope within the boundary of the river and the roadway. So we looked at what kind of structural elements we could use. One of them was drilled shafts, which would require quite a bit of soil removal, a lot of concrete work, reinforcement cages, and a lot of traffic in and out of site removing that clay. And we ended up stabilizing this slide with a concept using pin piles, which were basically 12-inch diameter pipe piles filled with concrete. And you can see within the model, we can insert those piles and we can calculate the stresses on those piles to design them and make sure that we've got enough capacity in them. So the resulting design was 12-inch diameter pipe piles that were concrete filled, and they were 2 rows of them. The rows were 8 feet apart and had a 10-foot spacing in between the piles. The piles were approximately 50 feet long, and if we go back to the cross-section, the till layer, which is really the hard layer in which everybody drives the piles to in the region, is about 80 to 85 feet down. We only drove these piles 50 feet down, and the benefits of doing that numerical analysis is that we were able to shorten the piles up such that we didn't need to weld sections on the piles, and you could deliver these piles to the site on a standard semi-truckload. So during the design phase, oh, I'm sorry.
I think it's me.
Yeah.
So at this point, we kind of have an idea what we're going to do to mitigate the slide, just as part of a typical part of our DOT process through the environmental document, the NEPA process. We go and we now need to have a public input meeting. So we're going through the process and how we're planning on mitigating the slide, and what some of the things the public brings up to us is they're very concerned about the vibrations that they felt during those previous construction projects in 2009 and 2016, and also the vibrations that they're going to feel during this pile driving process for our slide mitigation project. They're also concerned about being notified when pile driving is going to occur, the traffic impacts, and then they're also concerned about erosion and land loss on the north side of the river. So in addition to being concerned about these vibrations, there's a landslide on the north side of the river separate from our slide, and they're worried, they're losing some riverbank, they're having some damage to their homes from that, so they don't want our vibrations to make that worse. And we obviously don't want that as well. So, we listen to that feedback that we get from the public, and we kind of come up with a plan on how to mitigate those concerns and both protect the public's property and ourselves during this construction process. So They're concerned about the construction vibrations. We're concerned about those construction vibrations. We don't want to impact anyone negatively as well. So we kind of come up with a plan on how we're going to mitigate that. Aaron's group is going to do a vibration evaluation study on kind of how we expect the pile driving to create vibrations in this material for this project. And then we're going to set up a monitoring plan for that during construction. We're going to set some thresholds for the contractor to be required to stay under so that we know that we're not going to impact those structures around the site. We're going to monitor the vibrations during construction so we can kind of show that we're staying underneath that and then give the contractor feedback. We're also going to try and make sure that those are feasible thresholds so that the contractor can still complete the work and stay underneath those thresholds. And then we're going to do pre and post-construction structure surveys. So we're going to go out, we're going to look at the sites that people allow us into and kind of ascertain their condition before the project and then come back and check afterwards to kind of show that everything's the same, we haven't caused any additional damage. Then the traffic impacts, it's just a single lane closure for a maximum of 28 days. It's a relatively quick project. It's a relatively minor traffic impact. And then communication. So the consultant ended up assigning a person to the project to be specifically available to the public so they could get a hold of, ask questions. That person could talk to the material experts on the project and get them answers. And then also we could notify the public through that person on pile driving or any other construction activities that we need to.
So we were really fortunate because we had to assess, would these 12-inch diameter pipe piles negatively affect the neighbors in the area? And fortunately, there was a project going on with the high mast light poles nearby, and we were able to set out and develop a monitoring program where we could collect some data and use it for our study at our site. Although it was a different pile type, they were using 12 by 53s in the field for the high mast light poles, and ours were 12-inch diameter. We deemed that it was probably close enough to what we needed to do in order to come up with some kind of correlation that would work at our site. And what we found is that we set out vibration monitoring seismographs on the pile driving project at various distances away and collected data while they were driving at one of the high mast poles. And we collected a number of readings. What we found was that the peak particle velocity readings exceeded 0.2 inches per second. No peak particle velocity readings exceeded 0.2 inches per second at 200 feet. Most didn't exceed 0.2 at 100 feet, which is kind of a recommended damage threshold. Most readings at 50 feet didn't exceed 0.5 inches per second. And that'll be important later when I talk about how we set our thresholds for the project. But what we could tell is that over 400 feet away, you could still feel some of the pile driving. And so when we started thinking about it, that impacted roughly 31 homes or so in the area around our project site. So we took that data and we developed some correlations from the actual data we collected, compared that to correlations by a couple Caltrans and other investigators, and we developed kind of a plan for how far away we think these vibrations were going to be perceived at our site. And from there, we were able to develop a map. And we took this map and we kind of set out the distances. If you can see, this is about 500 feet away, this is 1,000 feet away, and we identified areas where we thought the vibrations would be slightly perceptible to strongly perceptible along the riverbank, North Riverbank. And we use this in designing a monitoring program for construction. Now, construction phase, I'm sorry, go ahead.
Yep. So at this point, Aaron's group has done the work on the vibration stuff. We kind of have a plan for what we're going to do going forward into construction. We've set thresholds. We kind of have a monitoring plan. So we kind of go back to the public. We have a second public input meeting where we kind of go over this vibration mitigation plan with them, try and ease concerns about the project. So kind of our general plan with that is that we're gonna have another public input meeting, or not an input meeting, but we're gonna have another meeting where we try and get people signed up for both the structure surveys and to install the seismograph instrumentation on their properties. And we want that in certain locations to be able to monitor that. We want people signed up for the structure surveys. We're gonna do some riverbank monitoring along with this. You know, one thing that we had, the public had concerns with is that existing instability on their riverbanks. You know, there is some issues with reduced instability during like seismic loadings or earthquakes, you know, which is a kind of a vibration-induced loading. We're orders of magnitude less on that front from a pile driving standpoint, so we're not concerned about kind of vibration-induced lack of stability for the landslide on the north side of the river. But we are gonna monitor that and kind of show that our construction activities don't line up with any additional movement there. And then we have our communication specialist that is gonna receive and respond to comments during construction.
So while Barr led the design phase work, SRF then switched over on the construction phase. And when we talk about some of the work that we had to do, we had to go through and notify all the landowners and offer them these pre-construction inspections and everything. Katie Laidley from SRF was the main contact that we had working with the homeowners, and it turned out to be super beneficial to have somebody local, somebody that could help us with all the scheduling. And one of the things we had to do is we had to request, are you willing to let us put seismographs on your property? Are you willing to let us in and do pre-construction and post-construction inspections? And it was helpful to have just kind of one point of contact on the project. So when we looked at trying to assess the vibration impacts, we went about identifying certain areas that we thought would be most important to install seismographs. And you can see those as the green triangles across the site. Some of these areas were, we were able to keep them there the whole time. Other areas, pieces and parts disappeared at night. So we had someone that was monitoring this remotely, all of the sensors from our Minneapolis office, and can tell when something disappeared or maybe a solar panel walked off because you ran out of power the next morning. And so he was constantly kind of watching what was going on, and we would have to have someone go out and kind of check on the sensors. But when we installed these seismographs, one of the most important things you have to do is we need to collect background data. We want to make sure that we've got good background data on what kind of vibrations they're seeing across the site already. And that could be from traffic, it could be from any other adjacent construction. And then once we get that, we move into the construction phase where we're doing construction monitoring, and we've set alert thresholds for the seismographs. And these alert thresholds are programmed into the seismograph, and then they will report back to our monitor in Minneapolis, but we'll also send messages out to the field staff out in the field. And along with that, we'd work with the contractor when we started exceeding some of these thresholds. But we also had set up a data hosting program and reporting so that the data was available quickly in the event that we had any exceedances. Another issue we had was the riverbank monitoring. And a number of these homeowners on this side were really concerned about this riverbank. So we set up a program where we had an automated motorized total station out in this field. And in fact, we had two of them at the start of the project, here and here, that worked basically on line of sight, shooting prisms that were mounted on that north riverbank. Over time, we transitioned over to installing tilt sensors as well in that area. And that is the result of the fact that the leaves came out in the trees. So you can't always see the prisms that you've already installed. So we put some tilt sensors in to the riverbank, and we could tell if the riverbank was sliding or moving into towards the river direction. And as part of that riverbank monitoring system, it's really important, again, to collect a lot of baseline data to make sure that as the river level goes up and down, is that affecting that riverbank more than the construction vibrations? And something to compare to when if we were to see any thresholds exceeded. During construction, we were collecting measurements with the automated total station along that riverbank, both before, during, and after construction. If we had some kind of exceedance or some kind of movement, somebody on site would go out and check the riverbank. They would look to see if there was any scarps developing and take measurements if something had moved. And then we provided a daily update during construction. We also had homeowners that were constantly doing their own monitoring of the riverbank as well on their property. The other thing we had to do, and can be quite a challenge, is these pre-construction inspections. Coordinating those and getting them scheduled, because we had a two-man crew that would go into each house. Getting that coordinated and scheduled with that crew, because it would take 4 to 8 hours to go through each structure, was really important. And some of the things that we're looking for are pre-existing damages to those structures. And this is a picture from one of the structures near the site. On the clays in West Fargo or in the region, they're very susceptible to settlement. And these structures, you'll see separation from block on the structures. And so those are the kind of things that we're looking for. We can document those ahead of time and rule them out, or we can assess whether they were caused by the pile driving. Now, Colter and I want to stress that the pictures that I'm going to show you here are not from the project. We decided that we would not include actual photos of people's homes from the project, but more of an example of the kinds of things that we were looking for on the project. We would send people through looking for cracks in drywall and measuring the width of those cracks ahead of time. There may be cracks in the facade of their home or some of the structures nearby, such as the school. We're looking for cracks in the foundations, and we're even looking for hairline cracks in the drywall and measuring those and documenting them with photos and video as we went along. And again, what we found is there were a number of structures that had this kind of structural damage of cracked walls, cracked foundations near the project site. This one's you.
So Aaron's group went through and, completed those construction surveys. The contractor was talking about starting in mid to late April, which is kind of earlier than we were anticipating for the pile driving. So his group really hustled to get all that stuff done. And then I believe that contractor was also working a significant amount on the diversion project, and kind of decided they were going to start on that first. So they ended up not starting driving pile until June 26th. But then, that went relatively quickly. That was the main part of this project, done by July 15th. But had the vibration and riverbank monitoring equipment removed by July 18th. Then all the repairs done by August 12th. So roughly a 2-month project. So it was relatively quick once things finally get going. This is just a picture of the pile driving process on the site. So like Aaron said before, these piles were just driven to 50 feet. We didn't really have any requirements for how that happened, besides that they stayed underneath the vibration thresholds. We don't have any hammer requirements. We're not counting blows or anything and trying to figure out an axial capacity. We don't have any axial capacity requirements. These are just laterally loaded pipe piles. So it was up to the contractor kind of what they wanted to do with that. They just needed to stay below our vibration thresholds. And then on the right, you can see the piles in place. Like Aaron said, these are closed-end pipe piles that we then backfilled with concrete. And then this has ended up getting backfilled, so you can't see any of these on site anymore. They're underground. It's just a little grassed area at this point.
So as part of the vibration monitoring program, we ended up with about 31 structures within 400 feet. We sent an engineering team up that has done a lot of pre-construction inspections in the past, and we would go through each of those structures as I discussed and document everything. And then we set up kind of vibration monitoring, post-inspection, and constant communication, I guess I would say, with the homeowners as they needed it. And that was one of the things that was really beneficial with kind of removing the engineering team from dealing with the homeowners and having somebody that's better at communication probably than an engineering team handle this. So when Katie was dealing with them, it worked a lot better than having our crew that was jumping around from site to site trying to deal with it. We had one point of contact that could take those concerns and help us deal with them. In the vibration monitoring program, we set some limits for this project of 0.3 inches per second peak particle velocity for the residential and retail structures that were primarily constructed out of drywall, and 0.5 inches per second for commercial structures. Commercial structures can handle quite a bit more movement without showing the damage, so we set that at a higher threshold. And the stop activity on the project, if you exceed 80% of that limit, and stop all of the work if it exceeds that, and come up with a new plan. And so one of the things that we had happen was we had 3 thresholds exceeded. And what we found, and you can see on, this is kind of a summary of one of the reports that we put out. We had 3 exceedances here, and I'll go into that in a second. But when we had that exceedance, the contractor by the construction documents was responsible for correcting any of the damages that occurred on the project. So when we looked at these random exceedances that we had, you could see this is kind of a typical report output. You can see the vibration data. And because we had pile driving monitoring going on in real time, we were able to compare this to what the actual pile driving traces look like. And we were able to identify that these random exceedances where somebody kicked a seismograph or something else might have occurred outside of the construction time period of the day. And we were able to rule that out so that the contractor could keep working. The riverbank monitoring program, since the contractor's schedule really extended into the summer, as I said, we had some issues. There really wasn't a good place to put the monitoring equipment, so we mounted the total stations on the riverbank, south riverbank of the project site, and set them up to run. But as time went on, the foliage came out, and we had some high river levels that actually flooded out one of the total stations. So we kind of had to transition, as I said earlier, to go from fully automated to manual observations and kind of a partially automated monitoring program. And so we looked at the data that we were collecting, and what we found is a pretty clear correlation between the river levels and how the river levels changed affected that north slope over time.
This one's you.
So, so as part of the construction monitoring summary, we ended up doing 21 pre-construction surveys at properties. They range from private homes to businesses, a church, school district administration building, and only 7 of those asked for post-construction surveys, so I would call that a success. No damages were documented, and we really didn't have any complaints from any of the adjacent homeowners.
So this is just kind of a project summary. You know, the public, you know, we kind of went through our typical landslide mitigation process during the public engagement portion. We kind of had another aspect of the project thrown in with the vibration thresholds and monitoring, but that was good. You know, we were proactive in kind of our site development, working through these thresholds, working with the public on this stuff, setting up this monitoring program, you know, doing those site inspections, kind of showing our work and doing our due diligence to show that we don't think our project is going to cause any issues with anyone else's property or assets, but we're going to do the work we kind of deem necessary to show that we're not going to damage any of that, and kind of protect everyone in the process. But with that, you know, we successfully mitigated the landslide. We didn't have any damages or complaints during construction, so I think we kind of view this as a pretty big success. But with that, does anyone have any questions? Yep.
Are those ones, the lots that you had that said city-owned, are those the lots that were bought out?
Yeah.
Are there still homes on those?
I think they're gone now.
They're demoed.
Yeah. As far as this area right here that you see in your photo, is that long-term monitoring in place, did you say?
We have
One inclinometer, isn't it?
I think we have 2. So we have 2 inclinometers in. We have one in one of the pipe piles and then one in between one of the pipe piles. So we have some long-term monitoring in place. I think it did in your background stuff, right? Railroad?
That's a good question. I don't remember. It may have.
I would think I remember that coming up during the kind of background monitoring. Okay, thank you.